I'm Miss Fung. Today we're going to look at combinations of any size. Let's do a bit of a warm-up. If you had 4 donuts and 5 cupcakes, how many different boxes of 6 desserts can be made? So first let's identify the number of objects. So the question is desserts. So we have 9 desserts altogether. And the number of spaces is 6. Order doesn't matter because we're picking desserts. So that means, do we use P or C? We would use C. So 9C6. And on the calculator, it gives us 84. There's another video for using the calculator. Click on the little I and it'll take you there. Example 2. How many different boxes containing 3 donuts and 3 cupcakes can be made? So we have 4 donuts, that's N for the donuts, and a space of 3. And for the cupcakes, we have N is 5 and a space of also 3. We want this and that, and therefore that's going to be times. So 4C3 times 5C3, which gives us 4 times 10 is 40 on the calculator. How many boxes of 6 desserts contain at least 4 cupcakes? So now we're picking 6 desserts and at least 4 cupcakes. What does that mean? It means we can have 4 cupcakes and 2 donuts because we want 6 desserts, so 4 and 2. Or at least 4 cupcakes means we can have all 5 cupcakes. And if we had 5 cupcakes, how many donuts will we need to make 6 desserts? There'll be 1 donut. Can we have 6 cupcakes? No, because we only have 5 cupcakes to choose from. So at least 4 cupcakes means 4 or 5. And because we have 4 cupcakes, we must pick 2 donuts to make the box of 6. And because if we have 5 cupcakes, we need 1 more donut to make the box of 6. So we can have this arrangement or that arrangement. What does and mean and what does or mean again? And means times and or means plus. So now we have N here is 5 for the cupcakes and R is 4. And N for the donuts is 4 and we're picking 2, so the space is 2. The cupcakes we have N and R is 5, and for the donuts N is 4, R is 1. So now we have 5C4 and times 4C2, and we have 5C5 and 4C1. So the ands are times and the or is plus. So this and this plus this and this. So put that in the calculator and you'll see that we obtain a total of 34 different boxes. What happens if we have 3 different flavors of ice cream, apricot, blueberry and chocolate, and we could choose any number of ice cream between 0 scoops to 3 scoops? Let's see if we can find an interesting pattern. How many combinations of any size, including none, could you choose? Well, if we had none, that's one choice. It is none. If we had to pick only one flavor, we could have apricot or blueberry or chocolate. That's 3. If we had to pick 2 flavors, these are the 3 combinations. And if we had to pick all 3 flavors, well, there's only one choice. So it will be 3C0, so 3 flavors, R is 0, 3C1, 3C2, and 3C3. So we can have this, or this, or this, or this. In other words, plus. If you add this all together, you realize it's 1 plus 3 plus 3 plus 1, which is 8. I wonder if you can recognize this pattern of 1, 3, 3, 1. It's another topic that we've done before. Now, if we looked at the number of scoops previously, we looked at no scoop, 1 scoop, 2 scoop, 3 scoop, we see that we obtain this pattern. But what happens if we focus on each flavor at a time? So, for example, we can have apricot or no apricot, then we can have I can't remember what B was, sorry, blueberry or no blueberry in our second option, and we can have chocolate or no chocolate. In this tree diagram, we see that we can have ABC or AC or BC or just B or just C or no flavor at all. So in this setup, focusing on the flavors instead of the scoops, we can see that we have 2 times 2 times 2 options, or in other words 2 to the power of 3 options, which is 8, which is the same as before. So we can look at the same problem looking at the number of scoops of ice creams, or looking at whether we scoop or not scoop each flavor. And we notice that the 2 are identical. So 2 to the 3 is the same as 3C0 plus 3C1 plus 3C2 plus 3C3. We can look at this and identify the pattern 0, 1, 2, 3. So for 3, between 0 and 3, we get 2 to the power of 3 when we add them together. Or in other words, we can have another formula now. 2 to the n is equal to NC0 all the way to NCN, where you add them together. Why is this useful? Because it's a lot faster to type that in the calculator than all of this. Especially imagine a question where n is perhaps 100. You don't want to sit here and type 100C0 plus 100C1 plus 100C2 all the way to 100C100. You just want to type in 2 to the 100. A question like that could sound like if you could choose 100 ice cream flavors between 0 to 100 scoops. That would take a long time, and that's a lot faster. Let's do example 5. Ella is making an invitation for her party and she has 7 friends to choose from. If she may choose to invite any number of friends from 1 to 7, how many possible party lists does she have? So she can have, out of the 7 friends, she can invite 1, or she can invite 2, or 3, or 4, or 5, or 6, or 7. Then we add them all together and then we can see how many combinations there are. However, we know that if we started at 0, we would have been able to just type in 2 to the power of 7. So is there a faster way to type this in the calculator? Yes, there is, because we identify that that is that section there. So if you subtract 7C0 from both sides of the equations, we can see that 2 to the power of 7 minus the 7C0 gives us all of that, what we wanted. So 2 to the power of 7 minus 7C0 is 127. You might want to have a look at this example again slowly. So to recap, this whole thing is 2 to the 7. So if I want between 1 and 7, I would do 2 to the 7 minus 7C0. And recall from the previous video, anything C0 is always 1. I'm going to leave you with this little question here. Have a go at using your calculator and see if you can find what it has, what pattern it has relevant to Pascal's triangle. So use NCR, type in lots of numbers and see if you can figure out why I have Pascal's triangle here. Thank you for watching and I'll see you next time. Bye!